So section 3.5 is on rational functions. And top page 1, right, gives the formal definition of a rational function. And as I stated, right, we've been working with rational functions all semester, but now we're going to, this entire section is dedicated to them. And a rational function by definition is a quotient of two polynomials. The numerator consists of a polynomial, and the denominator consists of a polynomial. Okay? And the domain of a rational function is a set of all real numbers except for those values of x that make the denominator equal to 0. And you have had to find domains of rational functions, right, all semester long. Okay. So, in example 1, right, these are two examples of rational functions. Right, in A, the polynomial in the numerator is of degree 1, in the denominator is of degree 2. And in B, the polynomial in the numerator is degree 3, and the denominator is degree 2. Okay. So for these two rational functions, right, we're going to find the domain and the x and y intercepts of the rational functions. Okay. Oh, so when you might find it advantageous to do like I did and draw a line down the center of the page to keep stuff from A separate from B. That's the way I set it up. Okay. So in A we have f of x is equal to 3 minus x over x squared minus 4. So with rational functions and finding the domain, we don't have to concern ourselves with square roots where x is under the square root. Okay? We only have to concern ourselves with the values of x that make the denominator equal to 0. So we can write the domain using inequality notation as x squared minus 4 can't equal 0. Right? If x squared minus 4 equals 0, then we're dividing by 0, and division by 0 is undefined. Well, the left-hand side is the difference of squares. It factors into x plus 2 times x minus 2. And if that product can't equal 0, that means the first factor can't equal 0, and the second factor can't equal 0. And then solving for x, we get x can equal negative 2, and x can equal plus 2. So the domain is all real numbers, except for minus 2 and plus 2. So in interval notation, the domain is from minus infinity to minus 2, union minus 2 to 2, union 2 to infinity. That is the domain in interval notation. Okay. All real numbers except for minus 2 and 2. Okay. The y-intercept is the easiest of the intercepts to find. You evaluate, remember, in finding the y-intercept, you set x equal to 0 and solve for y, right? So the y-intercept is equal to f of 0, right? Remember, function values and y values are the same. And so you just put 0 in for x on the right-hand side. You know, y is equal to 3 minus 0 over 0 squared minus 4. And you get y is equal to minus 3/4, or the point 0 minus 3/4, however you want to write it. Okay. any questions on the y-intercept? To find the x-intercepts, and actually I'm going to put the s in parentheses because there might only be one. Okay. So to find the x-intercept or intercepts, right, you know, you set y equal to 0 and solve for x, right? Well, y and f of x, right, are the same thing. So actually we just set f of x equal to 0 on the left. Okay. And we have the right-hand side, 3 minus x over x squared minus 4 is equal to 0. Okay. Now the denominator can't equal 0, right? The only way that this quotient can equal 0 is if the numerator equals 0. Right? You know 0 divided by a non-zero number like 5 is equal to 0. Okay. But there's no number that you can put in for x in the denominator that will make the left-hand side equal to 0. Okay. The only way this fraction, this quotient can equal 0 is if the numerator is equal to 0. So you just set the numerator equal to 0 and solve for x. So we have 3 minus x is equal to 0, minus x is equal to negative 3, or x is equal to 3. So x equals 3, or the 0.30 is the x-intercept in the graph of this rational function. Okay. The only way this quotient can equal 0 is if the numerator equals 0. There's no number you can put in for x in the denominator that will make the left-hand side equal to 0. Okay. All right. So if there's no questions, let's move on to B. It's a little more challenging. We have f of x is equal to x cubed plus 2x squared minus x minus 2 over x squared minus x minus 6. Okay. And you might want to leave this space to the right here, because we're going to the right here blank, because we're going to end up having to do some factoring. All right. So the domain is all real numbers, except for those values of x that make the denominator equal to 0. So in inequality notation, we have the denominator can equal 0, and the denominator factors into x minus 3 times x plus 2. So if this product can equal 0, that means x minus 3 can equal 0, and x plus 2 can equal 0. Then solving each inequality, we get x can equal 3, and x can equal minus 2. So in inequality so in interval notation, the domain is minus infinity to minus 2, union minus 2 to 3, union 3 to infinity. So that's the domain in inequality notation. Okay. And this you've done. This is like an exam 1 question, right? Exam 1 or exam 2, I can't remember. Finding the, right, you had to find the domain of a rational function. It was either exam 1 or exam 2, I can't remember. All right, y-intercept. Again, y-intercept is equal to f of 0, okay? And you'll notice that with polynomials in the numerator and denominator, when you put in 0 and for x in the numerator, each of these first 3 terms are going to equal 0, and you're just going to be left with the constant term minus 2. In the denominator, each of these first 2 terms will equal 0, and you're just left with the constant term minus 6. And so the y-intercept just ends up being minus 2 divided by minus 6. Okay. So y is equal to minus 2 over minus 6. So y equals 1/3, or the 0.01/3 is the y-intercept. Does everybody understand that? Okay. Well, when you find the y-intercept, it just ends up being the constant term in the numerator over the constant term in the denominator. Because when you put in 0 for x in each of these terms, those terms will equal 0. Okay. All right. Now, the x-intercepts are more difficult to find because we have to find the x-intercepts. Remember, we set the numerator equal to 0, and that's a 3rd-degree polynomial, right? So, in finding the values of x that make the numerator equal 0, we got to factor that 3rd-degree polynomial. We know how to do it, right? That's what sections 3.3 and 3.4 were all about. Okay. So, to find the x-intercepts, we got to set the 3rd-degree polynomial x cubed plus 2x squared minus x minus 2 equal to 0 and solve for x. Okay. Well, what's the possible rational zeros list? Okay, looking for a rational 0. Factors of the leading coefficient are plus and minus 1. Factors of the constant term are plus and minus 1 and plus and minus 2. So the possible rational zeros are plus and minus 1 and plus and minus 2. Well, you plug 1 in for x. You have 1 cubed plus 2 times 1 squared minus 1 minus 2. And you get, oops, I wrote minus x, I meant minus 1. And you get 1 plus 2 is 3, and 3 minus 1 minus 2 is 0. So x equals 1 is a 0 of our 3rd-degree polynomial, which means x minus 1 is a factor. So we can write our 3rd-degree polynomial as x minus 1 times the quadratic. And to find the quadratic, we divide the third degree polynomial by x minus 1 using synthetic division. Okay? Math is cumulative. Okay? So you never forget what you've already learned. You just bring it with you to the next subject. Okay? So 1 goes in the box, and then the coefficients of the third degree polynomial are 1, 2, minus 1, minus 2. Bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Minus 1 plus 3 is 2. 1 times 2 is 2. Minus 2 plus 2 is 0, right? So we have a remainder of 0. If you don't have a remainder of 0, something's amiss. So the 2 goes with 1, the 3 goes with x, and the 1 goes with x squared. Okay. So I have to erase this. So our third degree polynomial, that's why I told you to leave this blank, right? So you got a factor. Factors into x minus 1 times, or quotient down here. 1 times x squared is x squared. 3 times x plus 3 times x plus 2 times 1. And that's all divided by this quadratic. Okay? And we factored this quadratic. It factored into x minus 3 times x plus 2. Well, now this, does everybody follow what we've done so far? Okay. We found x minus 1 to be a factor of our third degree polynomial. And then using synthetic division, we were able to factor our third degree polynomial into x minus 1 times this quadratic. Okay. Well, this quadratic factors. So we have x minus 1 times, what's that? X plus 2 times x plus 1. Over x minus 3 times x plus 2. Now you will notice that there's a common factor in the numerator and denominator. Okay. And so if we were to set the numerator equal to 0 and solve for x to find the x-intercept, we would think there's an x-intercept at x equals 1, at x equals minus 1, and at x equals minus 2. We would be correct in saying there's an x-intercept at x equals 1 and at x equals minus 1. There is not an x-intercept at x equals minus 2. Does anybody know what's at x equals minus 2 in the graph of this rational function? It's a hole in the graph. When you have a common factor in the numerator and denominator, that creates a hole in the graph. Okay? So, we cancel out the common factors in the numerator and denominator, right? The x plus 2. We're left with x minus 1 times x plus 1 over x minus 3. This is called reduced form, right? When you cancel out the common factors. Okay. And you still have the y-intercept right at y equals 1/3 or 0 1/3. So x plus 2, what's happening there is that we have a hole in the graph. at x equals minus 2. Okay. So you set that common factor, x plus 2 equals 0, when you solve right, you get x equals minus 2. Right? That's the x coordinate for the hole in the graph. Okay. And to find the y coordinate, okay, you would plug in minus 2 in for x in the reduced form of f of x. Okay. So now to find the x-intercepts, we set this numerator equal to 0 and solve for x. Okay. We set this numerator, x minus 1 times x plus 1 equal to 0 and solve for x. Okay? And so when you do that, right, the first factor, x minus 1 is equal to 0, or the second factor, x plus 1 is equal to 0. And when you solve the first equation, you get x is equal to 1, is the x-intercept, or you can write it as the point 1, 0, okay? And then second equation, right, we solve for x, you get x equals minus 1, is the x-intercept, or the point minus 1, 0. So those are the two locations of the x-intercepts. So when dealing with polynomials in the numerator and denominator, you got to factor to make sure there are no common factors. Okay. All right. Any questions on that? Okay. So you flip over your page. In example 2, we're given the rational function f of x equals 2x plus 1 over x plus 2. And now last semester, I wrote all this stuff out on the board. Students had to copy it down. And I thought, this semester, I thought, you know what, it'll be easier to learn, I think, if I just filled everything out and we just went through it, okay, line by line. So you can see, right, that x equals minus 2 is not in the domain of this rational function, right? Because you set x plus 2 not equal to 0, and you get x can equal negative 2. Okay? So the domain is the set of all real numbers except for minus 2. But we're interested in knowing, what does the graph, when it talks about let's investigate the behavior of the function for the value of x near minus 2, we're interested in what does the graph look like for values of x close to minus 2. Okay. And so we're not, when we say values of x near minus 2, right, we're not talking about minus 5 plus 3, okay, for values of x near minus 2. We're talking about values of x that are really close to minus 2, like minus 2.1 and minus 1.9. Okay? And so down here on the left, right, I have a table of values. So here are some values of x, right, starting at minus 1.9. And each succeeding value of x is a little bit closer to the number minus 2. And in the second column are the corresponding values of y, okay, the function values. So these combinations of x and y are ordered pairs in the graph of this function. Okay? And you can see at x equals minus 1.9, right, the function equals minus 28. At minus 1.99, right, the value of the function is minus 298, and so forth. Okay? So as we go down the column of x values, right, each succeeding value of x is closer to minus 2. And then as we go down the column of y values, right, we see that each succeeding value of y is larger than the previous one in absolute value terms. Okay? Each one is more negative than the previous one. And so when this pattern happens, okay, as y continues to decrease as x gets closer to -2, we say that y is decreasing without end or bound in mathematics. Okay? And so in fancy mathematical notation, okay, we say that, and you were introduced to this notation when we studied limits, we say that f of x is approaching -infinity or decreasing without bound as x gets closer to -2 from the right. Remember, the plus sign means from the right. And -1.9, right, is to the right of -2 on the real number line. So each of these values of x, right, are getting closer to the number -2 from the right. Okay. Conversely, instead of f of x, we can put in y, because y and f of x, right, are the same. Y and function values are the same. And right, y decreases without bound as x gets closer to -2 from the right. Okay. All right, so this is the behavior of the graph of the function f of x as x gets closer to -2 from the right. Okay. Now, in the next table, we have values of x that are to the left of -2, right? That are less than -2. And so in my column of x values, I start at -2, and then each succeeding value of x is a little bit closer to -2 from the left. Okay, so we're starting here at -2.1, and we're getting closer to -2 from the left. Well, in the next column are the corresponding values of y, the function values. You see at x equals -2.1, the function value is 32. At -2.01, the function value is 302. At -2.001, the function value is 3002, and so forth. And you can see that as the value of x gets closer to -2, the value of y is getting larger and larger and larger. Right? It's increasing without end or bound. And so in fancy mathematical notation, we write that f of x is going to infinity or increasing without bound as x gets closer to -2 from the left. Okay. We're approaching -2 from the left up here. Okay. And conversely, we can write y is increasing without bound as x approaches -2 from the left. Okay. So when you have that kind of behavior in the graph of a rational function, okay, we have what is called a vertical asymptote. I have that graphed over here. You can see here's -2 on the x-axis. And as x approaches -2 from the right, we said y decreased without bound. And so you can see that the graph is going down to the right of -2. And over here, values of x to the left of -2, we said the value of y was increasing without bound, and you can see that the graph is going up to the left of the vertical line, x equals -2. So when you have that kind of behavior, the vertical line, x equals -2 in this case, is called a vertical asymptote. Okay. Any questions on that? All right. And we're also asked to investigate the behavior of the function as x becomes large positive and negative. And that is referring to end behavior. Okay? And we studied end behavior with polynomial functions. So we're going to study end behavior with rational functions. So again, I have a table of values. So first we're going to start looking at large positive values of x, what the behavior of the graph is for this function. And so in my first column, I get values of x starting at 10, 10, 100, 1,000, 10,000, right? And you can see my values of x, right, as I go down the column. Each succeeding value of x is larger than the previous one. As I go down the column, right, the values of x are increasing without and or bound. That means we're going further and further and further out to the right on the x-axis. Well, the corresponding y values or function values, right, at x equals 10, y equals 1.75. At x equals 100, y equals 1.97. And you can see each succeeding value of y for each succeeding value of x is getting closer and closer to the number 2. So in fancy mathematical notation, we write the function f of x, right, approaches the number 2 as x increases without bound, or goes to plus infinity. And conversely, you write y approaches the number 2 as x increases without bound. Now for the left-in behavior, okay, we look at large negative values of x. So I started at minus 10, then minus 100, then minus 1,000, and so forth. And you can see that each succeeding value of x, right, is larger in absolute value terms than the previous one. Okay? And you can see, right, as x decreases, right, it's decreasing without bound, right? So we write x is decreasing without and or without bound. In the second column are then the corresponding values of y, the function values. And you can see that as x decreases without bound, the values of y, each succeeding value of y, is getting closer and closer to the number 2. Okay. So in fancy mathematical notation, we write f of x approaches the number 2 as x decreases without bound, goes to minus infinity. Conversely, we can write y approaches the number 2 as x decreases without bound, goes to minus infinity. Okay. So graphically, this is what's happening, right? As x increases without bound, the graph is getting closer and closer to the horizontal line, y equals 2. Right? The y value is getting closer to 2. And on the left end, as x decreases without bound, the y values are getting closer to 2. Okay? So this type of phenomenon, right, in this case the horizontal line y equals 2, is what is called a horizontal asymptote. Okay? So up above we have a vertical asymptote, where the graph either goes up or down on each side of the vertical line. And down here, we have a horizontal asymptote, right, where the graph gets closer to that horizontal line, either going out to the right and or to the left. Okay, so that's what horizontal and vertical asymptotes are. Okay. Any questions on that, ladies and gentlemen? So if you flip over your document, your handout, this part up here, right, this part right here talks about, gives you the formal mathematical definition of a vertical asymptote. And this part down here gives you the formal definition of a horizontal asymptote. Okay, so we just demonstrated that definition of vertical asymptote, horizontal asymptote, with the example on the previous page. Okay. And then there's a third kind of asymptote, which is under this special case, and it says if the degree of the polynomial in the numerator is exactly one more than the degree of the polynomial in the denominator, then the graph of the function has a third kind of asymptote, which is called a slant asymptote. Okay. So the numerator, if it's of degree n plus 1, then the denominator is of degree n, right? The numerator has a degree 1 more than the degree of the denominator. And if that's the case, then the equation of the slant asymptote is that of a straight line. In this case, I write it as y equals mx plus b. So this is the equation of a line in slope intercept form. Okay. And how we get the equation of that line for the slant asymptote is we have to do division. We have to divide the two polynomials. Sometimes you can use synthetic division, and sometimes you got to use long division. Okay. All right. I don't want to rush through example 3, but we'll pause right there. Okay.